Hi, everybody. I'm Denny Dahl from IonQ, and I'm going to introduce the third problem of the SKKU 2024 Quantum Challenge. We're going to analyze the Heisenberg spin glass using techniques from quantum computing. You might want to follow along with the problem right up here as I describe the challenge. If you've never heard of a spin glass before, here's a great reference from Wikipedia. The key thing to know about a spin glass is that it exhibits disorder, and so it's very challenging to find its low energy states. Our challenge problem combines a spin glass with a quantum Heisenberg model. Here's a great reference for the Heisenberg model. This is a system that has been studied by condensed matter physicists for a long time. The first thing we're going to do is look at a Heisenberg model defined over 4 spins, each of which is a spin 1/2 quantum degree of freedom. The interaction between each spin pair is a sum of 3 products, a poly x for the first spin multiplied by a poly x for the second spin, and similar terms for y and z. We will multiply these 3 terms by a weighting factor, jij, which is either +1 or -1. This is a static model, and so we can extract its spectrum using a numerical package like SciPy in a Python program. The first part of the challenge is to characterize the different models that we can build. There are symmetries that allow us to treat some of these models as equivalent. One symmetry is spin interchange, and the other is sign inversion. You'll figure out how many symmetry classes there are for this model in the first part of the challenge. Next, we analyze these same models using the adiabatic theorem. Here's a reference which provides background on the adiabatic theorem. In essence, what it says is that we can prepare the ground state of a simple Hamiltonian and then gradually change the Hamiltonian to a different one, while the system remains in its ground state. You will work out how the eigenvalues of our model systems change as the Hamiltonian evolves from a simple starting point to the Heisenberg model. Here's an example of how the energies change in one system. Applying the adiabatic theorem directly to the Heisenberg model does not work, and there are some interesting reasons for that. Essentially, it's because the Hamiltonian for the Heisenberg model commutes with the mixer operator, which drives the adiabatic evolution. We will modify the Heisenberg model by adding a linear term to it. This linear term gives a non-zero commutator and also makes the ground state unique. This gives us the model that we'll call the Heisenberg spin glass. You'll apply the adiabatic evolution to this model. There are 2 parameters that govern the behavior of the evolution, the total time and the number of time steps into which the evolution is decomposed. Find suitable values for these parameters that give 3 decimal place accuracy for the probabilities of the exact ground state. Given these parameters, you'll estimate the depth of the quantum circuit which carries out this computation. Do you think it's realistic? For the last part of our challenge, we will approach the problem of synthesizing the ground state for the Heisenberg spin glass directly. First, we'll note that the ground state is confined to a subspace of Hilbert space that has Hamming weight 3. In other words, the basis states that appear in our ground state all have 3 qubits turned on and 1 turned off. This observation allows us to guess a structure for the circuit that will create the ground state. The circuit will first move our initial state into the Hamming weight 3 sector. Then we will rotate within that sector to find the ground state. There is a class of mixer operators which rotates qubit states while keeping them in the same Hamming weight subspace. These mixer operators are called XY mixers. Here's one paper that describes their use. To complete this part of the challenge, you'll need to figure out the rotation angles in the XY mixer operators. You'll generate the 16 by 16 matrix capturing the final state of the circuit as a function of the three angle parameters for the three XY mixers. Then use a minimization routine, such as SciPy's minimize, to tune the angle parameters. You should find values for the three angle parameters that cause the probability vector for the circuit's output state to match the exact eigenstate of the Heisenberg spin glass. Now that you have the three angle parameters, construct a circuit that produces the correct output state up to probability. Verify that the probability of producing each computational basis state matches the probability with which that state occurs in the exact ground state. There is one last step so that the circuit produces the correct eigenstate. We have to check the relative phases of the non-zero basis states. If these are not already correct, find an RZ operator that produces a phase rotation of these states. Now that our circuit produces the exact ground state of the Heisenberg spin glass, we'll verify that we can measure the ground state energy using the circuit. Since the Hamiltonian contains terms that are not diagonal in our computational basis, we'll have to make measurements in three different computational bases to evaluate the Hamiltonian. There are simple single qubit operators we can apply to the end of our circuit to rotate into the computational x basis and y basis. Summing over all three bases, you should be able to reproduce the energy computation from the direct eigensolver. I hope you enjoy working on this challenge. I don't think it's easy. I certainly learned some interesting things as I set the problem up and solved it. I'm looking forward to receiving your answers. Good luck.